Good morning, students. So in the previous tutorials we saw that by using the three principal gates, the AND gate, OR gate and the NOR gate, these are the three principal gates. So using these three AND gate, OR gate and NOR gate, we can build many other types of logic gate functions such as NAND gate, NOR gate, or any other type of digital logical function that we can imagine. But there are two other types of digital logic gates which are, although they are not a basic gate in their own right, as they are constructed by combining together other logic gates, their output Boolean function is important enough to be considered as complete logic gates. These two hybrid logic gates are called exclusive OR, also called the XOR gate, and its complement, the exclusive NOR gate. So these two hybrid logic gates, exclusive OR and the exclusive NOR gate, is also most important enough for creating Boolean output functions. So in this session we are going to learn about the exclusive OR gate. So what is an exclusive OR gate or an XOR gate? Exclusive OR gate, it is sometimes called as EOR, XOR, EXOR and pronounced as exclusive OR. It is a digital logic gate that results in true, that is either 1 or high output when the number of true inputs is an odd count. That is the digital logic gate that results in true when the number of true inputs is an odd count. When the number of true input is an odd count, the output will also become true. An XOR gate implements an exclusive OR. That is, a true output result if one and only one of the gate inputs is of true. If both the inputs are false, false means either 0 or low, or if both are true, they result in a false output. So listen, exclusive OR generates a true value only if the input value, true inputs, is in an odd count. So a true output result if one and only one of the gate inputs is of true. If both the inputs are false or if both are true, they result in a false output. The XOR represents the inequality function. Inequality function means that is the output is true if the inputs are not identical. The outputs are true if the inputs are not identical, and then the output is false. An easy way to remember XOR is that it must have one or the other, but not both. It must have the input values one or the other, but not both. So XOR can also be viewed as an additional modulo 2. Resultantly, XOR gates are used to implement the binary addition in computers. A half adder has an XOR gate and AND gate. Other uses includes comparators, subtractors, also the controlled inverters makes use of this XOR gate. So the figure shows a 2-input XOR gate. As you see in the figure, there are two inputs A and B, and the result of this XOR gate is obtained as Q. So the Boolean expression obtained here is Q equal to A XOR B. See the truth table. If the value of both A and B are 0, Q value is also 0. That means the XOR gate produces a 0 output or low output if both the inputs are low. If any one of the input values is high, the output also becomes high. If A alone is high, the Q value is also high. If A is 1, Q is also 1. Like that, similarly, if B alone is 1, Q is also 1. So that means the XOR gate produces a high value only if any one of the input value is high. Otherwise 0. If both the input values are low, the result also becomes low. If both the input values are high, the result again will be low. So it can give a high output only if any one of the input value is high. So I said it earlier, an easy way to remember the XOR gate is A or B but not both gives Q. A or B but not both gives Q. So if any one of the value is high, the XOR gate results in a high value, otherwise low value, that is 0. So it produces a Boolean function Q equal to A XOR B, that is Q equal to AB dash plus A dash B. This is the Boolean expression obtained from this exclusive OR gate, Q equal to AB dash plus A dash B. As I said earlier, XOR can also be viewed as an additional modulo 2. XOR gates are used to implement the binary addition in computers. That means it can be used in a half adder. The Boolean expression itself makes it clear that it can be used in half adders or subtractors, comparators and controlled inverters. We use many symbols for OR gate. Commonly, there exist 3 schematic symbols for XOR gates. They can be given as the traditional ANSI symbol, DIN symbol and IEC symbol. In a few cases, the DIN symbol is used with the or commonly used plus symbol inside the circle symbol, XOR symbol. So some C-like languages uses a caret symbol also to represent a bitwise exclusive OR. It is to remember that the caret does not denote the logical conjunction AND in these languages despite the similarity of the symbol. So this language, C-like languages, uses caret symbol also to represent exclusive OR. For a 2 input, it is important to remember that for a 2 input OR gate, if A equal to 1 or B equal to 1 or both A plus B equal to 1, then the output from the digital gate must also be at a logic level 1. And because of this type of logic gate is known as an exclusive OR function. That you know from our early classes, we learned that for a 2 input OR gate, I am saying about the OR gate. For a 2 input OR gate, if A equal to 1 or B equal to 1 or both A plus B equal to 1, then the output from the digital gate must also be a logic level 1. And because of this type of logic gate is known as an inclusive OR function. The logic gate gets its name from the fact that it includes the case of Q equal to 1 when both A and B equal to 1. If however an logic output 1 is obtained when only A equal to 1 or when only B equal to 1 but not both together at the same time, giving the binary inputs of 0 1 or 1 0, then the output will be 1. This type of gate is known as an exclusive OR function. or as I said earlier, most commonly XOR function for short. This is because its Boolean expression excludes the or both case of q equal to 1 when both a and b equal to 1. In other words, the output of an exclusive OR gate only goes high when its two input terminals are at different logic levels with respect to each other. An odd number of logic 1s on its inputs gives a logic 1 at the output. These two inputs can be at logic level 1 or at logic level 0, giving us the Boolean expression of q equal to a XOR b. Q equal to a XOR b, that is equal to a dot b dash plus a b dash. The exclusive OR gate function or XOR is achieved by combining standard logic gates together to form more complex gate functions that are used extensively in building arithmetic logic circuits, computational logic comparators, and other error detection circuits. So it is an the two input exclusive OR gate is basically a modulo 2 adder, since it gives the sum of two binary numbers, and as a result are more complex in design than other basic types of logic gate. That is, you have seen that truth table and the logic simple, and the Boolean function obtained from this gate. So here is another 3 input XOR gate. Similar to the 2 input XOR gate, the 3 input XOR gate, the 3 input values are A, B, C, and the result of this 3 input XOR gate is Q. Here we see if the 3 input values A, B, and C are low, the result will also become low. The result, that is Q value, becomes high only if any one of the input value is high. Otherwise, the value will be 0, and there is an exceptional case that if all the input values are high, it obtains a high value. That is, if the number of high values in the input side is an odd count, the result will also becomes high. If either or if any one of the input value is high, the output will also becomes high, and if for 3 input XOR gate, if all the input values are high, the output will also becomes high. That is what I said. For a high value count is odd 1. If the input high value count is an odd count, then the output also becomes a high. Any odd number of inputs gives Q. That is an easy way to remember the truth table. Any odd number of inputs gives Q. And the Boolean expression here obtained is Q equal to A XOR B XOR C. That is Q equal to A B C dash plus A dash B C dash plus A B dash C plus A B C. From this Boolean expression, we can derive the logic circuit. So this ability, that is from the truth table itself, it is clear that the output of an exclusive OR gate only goes high when both of its two input terminals are at different logic levels with respect to each other. If these two inputs A and B are both at logic level 1 or both at logic level 0, the output is a 0, making the gate an odd but not the even gate. An odd gate but not the even gate. That is, the output is 1 when there are an odd number of ones in the inputs. This ability of the exclusive OR gate to compare two logic levels and produce an output value dependent upon the input conditions is very useful in computational logic circuits, because it produces such a Boolean function. It is useful for useful for other logic combinations also. The logic function implemented by an 2-input XOR gate, it is given either as A or B, but not both, will give an output at Q. In general, XOR gate will give an output value of logic 1 only when there are an odd number of ones on the inputs to the gate. If the two numbers are equal, the output is 0. So this is then an XOR function with more than 2 inputs is called an odd function or modulo 2 sum. Mod 2 sum, not an XOR. This description can be expanded to apply to any number of individual inputs as we seen for a 3-input XOR gate. And we have said about the simples applied for the XOR gate. Here is another XOR gate equivalent circuit, that is an XOR gate implemented using an OR gate, NAND gate and AND gate. This logic circuit is equivalent to an XOR gate. That is first we make use of 2 input values here, and it is applied to an OR gate and NAND gate, and the result of this OR gate A plus B and the result of the NAND gate AB dash is both taken as input values for the AND gate, and the result obtained will be Q equal to A plus B dot AB dash. This is of course the exclusive OR gate. So an exclusive OR gate can be implemented in this way also, using an OR gate, NAND gate, and the input from this OR and NAND gate will be applied to an AND gate. The result will be Q equal to A plus B into A B dash. It is an XOR gate equivalent circuit. One of the main disadvantages of implementing the exclusive OR function above is that it contains 3 different types of logic gates, OR, NAND and finally AND within its design. One easier way of producing the exclusive OR function from a single gate is to use our old, as we saw earlier, in our NAND gate. So exclusive OR are used mainly to build circuits that perform arithmetic operations and calculations, especially for adders and half adders, as they can provide a carry bit function or as a controlled inverter, where one input passes the binary data and the other input is applied with a control signal. Commonly available digital logic exclusive OR gates include TTL logic exclusive OR gate, CMOS logic exclusive OR gates, etc. So as I said, there are many more applications of XOR gate. There are numerous counts of various applications of XOR gate. One of the applications of XOR gate is that it can be used as a 1-bit adder that adds any of the 2 bits together to produce 1 bit as output. For instance, if we add 1 plus 1 in binary, we can expect a 2-bit answer. That is 1 0. It means 2 in decimal. Because the trailing sum bit in this output has been achieved with the XOR gate, the preceding carry bit is calculated using an AND gate. This is the primary principle in half adders. A slightly larger full adder circuit can be chained together to add longer binary numbers. The PRN, that is pseudo random number generators, specifically called linear feedback shift registers, are described in terms of the exclusive OR operation. Thus, a suitable setup of exclusive OR can model a linear feedback shift register to generate random numbers. The exclusive gates form a 0 output when both inputs are matched. We learned from this class. An exclusive OR gates forms a 0 output when both inputs are matched. When searching for a PRN sequence or a specific bit pattern in a very long data sequence, an XOR gate series can be used to compare a string of bits from the available data sequence against the target sequence in parallel. Then the number of zero outputs can be counted to determine how the data sequence matches the target sequence well. Correlators are used in various communication devices such as CDMA receivers and decoders for channel codes and error correction. In a CDMA receiver, the correlators are used for polarity extraction of a particular PRN sequence out of a combined collection of the PRN sequences. So these are all some applications of XOR gate. I hope it's clear for you. Learn well. Thank you.